In traditional direct volume rendering, a ray is shot from each pixel into the volume. Typically, the volume is stored as a regular grid. Along the ray, the density value is fetched from that grid via trilinear interpolation and converted to a color via transfer function. The colors are then accumulated for each step along the ray and blended together. This method is fast to render, but storing the volume grid requires a lot of memory. As an alternative, scene representation networks replace the volume grid by a fully connected network. Instead of interpolating the volume grid, the network is evaluated at every step. This allows for a very compact representation, but computation times become an issue. How can we make those networks fast? Let's first have a look at a very simple model of the GPU. The first block is the global memory, where all the data is stored and which can be accessed by the CPU. Modern GPUs have multiple gigabytes of global memory. The computation cores then are organized in multiprocessors. Each multiprocessor executes 32 threads in a SIMD fashion. Additionally, there is 48 kilobytes of programmable shared memory per multiprocessor that is magnitudes faster than global memory. But this memory can only be accessed by the threads in the current multiprocessor. When evaluating neural networks with TensorFlow or Python, the current states are loaded from global memory, a single layer is computed and the results are written back. This involves a lot of memory reads and writes. We show that if the network weights and hidden states can fit within the 48 kilobytes of shared memory, the network can be evaluated without any global memory access. These are the networks that fit within this memory limitation. Shown here are the execution times when rendering an image of resolution 512 to the square with the neural network. PyTorch allows the computation to be performed with 16-bit half-precision floats instead of regular 32-bit floats. This already improves the performance. With our custom implementation, however, we can again improve upon that. Small networks, like 2 layers with 32 hidden channels between the layers, can be rendered in 90 milliseconds. That is a speed up of 8.6 over 32-bit PyTorch or 6.3 over 16-bit PyTorch. However, the quality of the reconstruction is suboptimal with those small networks. Larger networks lead to greatly improved reconstruction quality, but are also substantially slower to render. For example, with 6 layers and 64 hidden channels, an image requires almost 2 seconds to render. This is one of the largest networks possible within the limitations of the shared memory. How can we achieve high quality while still using small networks for fast renderings? For that purpose, we introduce volumetric latent grids. A coarse grid with learned values is first placed over the object. Then, when evaluating a sample position along the ray, the contents of this coarse grid are interpolated and passed on to the network as additional input. This opens up a 2-dimensional parameter space, where the trainable parameters are split between the network and the volumetric latent grid. As shown earlier, small networks without a latent grid lead to a loss of detail. Introducing the latent grid drastically improves the quality. As a comparison, this is the rendering when only a grid with the same memory requirements as the latent grid is used, without a network. So this is what one would see if the volume is rendered traditionally with a lower grid resolution. As one can see, the combination of a latent grid with a small network leads to the best results. Next, we demonstrate our approach for time-varying data. Here you can see the Bloom dataset from timestamp 30 up to timestamp 100. First, we assign a latent grid at every 10th timestep. For in-between timesteps, the grid is linearly interpolated. Second, for training, every 5th timestep is passed to the network. The training network is shown here in the middle. As one can see, the network accurately reconstructs the trained timesteps and even learned a semantically plausible interpolation. For comparison, if we take the original volume at the keyframes and interpolate those grids, the interpolation is much less plausible. This also shows in the SSIM statistics at the bottom. We want to highlight here that with our approach of interpolating the latent grid, arbitrary fractional time steps can be used. This can be used, for example, for a super slow motion. Here are the results for the two additional datasets presented in the paper. First, the ejector dataset. And the Richtmeier-Meshkov dataset. Thank you for your attention.